All right, thank you. And this is a joint project with Winnie Lee and Fang-Ting. We have the article posted very recently to archive. So this is actually kind of longer than 50 minutes if I want to talk about everything. So I will focus on more like the backgrounds and motivations. And so the topic is on hypergeometric functions. The classical ones are special functions with a lot of symmetries that they play very important role in physics, number theory, and combinatorics. And more recently, there is a development under the umbrella called hypergeometric motif. So there are several different topics can be unified under the umbrella, including the classical hypergeometric functions and differential equations. And there are hypergeometric Galois representations and the corresponding L functions. So this is firstly developed by Katz for our finite fields and extended to more globally. And on the computation side, David Roberts, Rodriguez Villegas, and Mark Watkins, they actually implemented a lot of useful functions to MATLAB and use that to construct very kind of special L functions to test standard conjectures. And also more on the local finite field side, there are many hypergeometric character sums. And John Green starting the project of hypergeometric function over finite fields, and later was modified by Dermot McCarthy, and further by Fritz Boykers, Harry Cohen, and Anton Menick. And in 2014, my collaborators, Jenny Fuseli, Ravi Ramakrishna, Hollis Wisher, and Fang-Ting, we have approach to those finite field character sums using a perspective parallel to the classical setting. And we attain a lot of identities, which we use to compute the invariance of hypergeometric varieties. And more recently, Bill, Dr. Hoffman, and Chu, they actually use rigidity of hypergeometric system to attain such identities more systematically. There is also the p-adic side, which is relating to de Waals approach to unit roots. And based on de Waals approach, the further kind of more stronger version called supercongruences. So they appear in the work by Scott Algren, Ken Arnold, etc. So myself and Ravi Ramakrishna, we have a systematic way of using classical hypergeometric functions to attain or to prove supercongruences. And in my another recent work, joined with Fang-Ting, Noriko Yuri, and Vadim Zhugeling, we attain conjecture, supercongruences conjecture by Rodriguez Villegas occur to rigid Calabi-Yau three-folds. But I'll be focused on more on the formulas, okay, which is Whipple's formula. So the major motivation I want to mention, at least to myself, is the hypergeometric machineries are very explicit. And there are many existing beautiful formulas in the literature, including Clausen formula and one of the Repost formula I'm going to talk about. But there are several others. And we like to interpret those formulas in other settings I mentioned over the L-adic setting, p-adic setting, and finite field setting, and use them to construct special Galois representations and solve open conjectures. So a particular motivation for this talk is actually use identities to construct hypergeometric motifs or Galois representations, which is decomposable. And so I'm going to mention this conjecture of David Roberts and Rodriguez Villegas later. So this will give a connection to supercongruence. So I'm going to give you more details about this motivation later. So here's some of the notations we're going to use. On the classical side, one of the very basic player is the gamma function. So you can define gamma function using this integral and which is integration for given x. You can do the integration of t, so dt over t. And once give you an x, fix x, t of x is going to be an multiplicative function of t. And this part, e of minus t, is an additive function of t. And gamma functions such satisfy the functional equation, so which is actually the analytic continuation of the factorial function. It satisfies two very useful formula. One is called the refraction formula for A, which is a complex number. If you multiply gamma A and gamma 1 minus A, what you're going to obtain is going to be, if A is going to be a rational number, you're going to get a algebraic multiple of pi. And the other formula is called multiplication formula. So if you fix A, which is a complex number, if you multiply gamma A, and then gamma plus 1/2, which is a phase shift by 1/2, what you're going to get will be relating to gamma of 2 times A, so it's double. And then in addition, there's gamma 1/2. There are other multiplication formula. Here it's only double. You can kind of imagine what the formula, if I change it to 3 or 4, may look like. But they look similar. On the finite field side, so if we switch setting to finite fields, there is a player playing the role of gamma function. So let's do the setup over here. If we have a finite field, okay, it's denoted by FQ. So it's going to be size a finite field of Q elements of characteristic P. And in my talk, I'm going to assume that P is going to be odd. And if you consider all the homomorphism from the invertible elements of this finite field to invertible elements in C, they're forming the character group of this finite field of invertible elements. It's a cyclic group. So I will use omega to denote one of the generators. And once you fix a generator for any other multiplicative character, it's going to be a power of this omega. And for such a chi, you can define the corresponding Gauss sum. The Gauss sum is defined as using this multiplicative character you're applying to all the invertible elements in your finite field times, so this is additive character. So how you attain it is you're going to fix a primitive piece root, and then you're going to take the trace function of this element. For each individual element, you take a trace function from FQ to FP. And so you get a value which is an inside FP, and then you take the zeta P raised to that particular value. So it's actually corresponding to the multiplicative and the additive characters on the Gauss sum, the gamma function. So it's actually well known that Gauss sum, they satisfy also refraction and multiplication formula. They are finite field analogs of the gamma function. Okay. So now I'm going to get to the basic setup over here. So if I mention about a hypergeometric data, I'm actually referring to a triple of 3 elements. Alpha is a multi-set consisting for this type of rational numbers. And beta is another multi-set of the same cardinality. The numbers could be the same, but the convention will be inside beta, the first element, I'm going to set it to be 1. Otherwise, you can do a normalization. And for most of the cases, the AI and BJ are going to be rational numbers, or you can even further take their modulo z, so consider to be the values within 0 and 1. And the last one, lambda for most of the application later will be either inside rational field of rational numbers or its algebraic closure, or more generally, you can consider lambda to be a complex number. Once you give such a pair of multi-sets, we're going to let the least positive denominator of all the AI and BJ to be capital letter M. For instance, here I have 1 alpha consists of 3 elements, 1/2, 1/3, and 2/3. So the capital M for this case is going to be 6, which is the least common denominator of AI and BJs. So for such a pair of alpha and beta, the couple is said to be primitive if the difference of each AI and BJ is not inside the set of integers for all the ij. And another notation will be a set, like this one down here, 1/2, 1/3, 2/3. It's said to be defined over Q. So the notation, I'm going to use /Q to be defined over Q. If you look at the corresponding polynomial, which is obtained by using a formal variable capital X and minus e to the 2 pi I, which is square root minus 1 times aj. For instance, if you look at this particular multi-set, so it's going to be defined over Q, consists of x minus 1 and also the cyclotomic polynomial of degree 3 over here. And if you put together for the hypergeometric data, it's said to be defined over Q if both alpha, beta are defined over Q, and so is lambda. Lambda is going to be a rational number. And another notation I will use is the notion the pair alpha beta is said to be self-dual if, for instance, over here for alpha, it is self-dual because if I look at minus alpha modulo z, I will get back 1/2. I get back the minus 1/3 will be 2/3. Minus 2/3 modulo z is 1/3. So I get back the same alpha up to a permutation. So alpha is said to be self-dual. Okay, so these are the basic notations. Is there any questions before I continue?
What exactly do you mean by congruent? Like for the sets to be congruent?
Modulo, say congruent, modulo z over here means.
Okay, I see.
Say 1/3. If I take minus 1/3, it's minus minus 1/3 modulo 1 or plus an integer plus 1, you get 2/3. That's what I mean over here. Because over here, if you add some integer to the exponent, it doesn't quite matter. So that's why the AI, in the end, I only worry about the values of AI up to some integer multiples. Did I answer your question?
Yeah, you did.
All right. Okay, so let's continue with the notation. We're going to look at the corresponding functions. So over C, over the complex setting, so there is the classical hypergeometric function. So for fixed lambda or fixed alpha, beta, which are the multi-sets of lambda, it's going to be a formal power series. So the formal power series you use, you put them together as power of lambda. The power goes from 0 to infinity, and the coefficient in front of lambda to the k will be this. This is the ingredient. You put together the AIs from alpha to the top, forming so-called the rising factorial. So A sub k is going to be A times A plus 1 and all the way to A plus k minus 1. And the notation over here, if you get to 0, A sub 0 is going to be 1 because you can also define alternatively using the gamma function. And the contribution of B goes to the denominator. So you make, essentially over here, it's a rational number. So you put a formal power series. Now, if you treat lambda as a variable, if you treat it as a variable, then it satisfies an ODE. Degree of the ODE will be the multiplicity, the length of the multi-set alpha. And this ODE is so-called hypergeometric functions. It has only 3 singularities at 0, 1, and infinity. And one of the useful things to us is if you look at this ODE, if you look at the local holomorphic solution away from 0, 1, infinity, you pick any other point. You can use Frobenet's method to do the local solution. And the local solution is going to be the dimension. It's a C vector space. The dimension is going to be the length of the multiset alpha, which is the same as beta. So this is the complex setting. You have a classical hypergeometric function. Another notation I will use is the truncation. It's very similar to the formal power series. If there is a subscript attached to the formal power series, it only means that the summation will truncate from k from 0 all the way to the subscript n over here. And now, if we further go down to the finite field setting, we're going to use the dictionary. The dictionary, basically, the thing to remember is gamma function corresponds to Gauss sums. So now, if I have A, which is going to be a rational number, if in the case we have A is going to be the denominator, it's going to be a divisor of this capital M. If I have a finite field whose size is going to be 1 modulo this capital M, which is the least common denominator, then Q minus 1 times A is going to be integer. This omega, as mentioned before, it's the generator for the multiplicative characters of this finite field. So you have a character raised to an integer power. You have an character. Then you can compute the Gauss sum using the recipe in the previous slides. And put together, if you have alpha and beta, you can come up with a character sum. So the character sum is going to be a finite field analog of this complex setting up here. We're going to sum over basically all the characters, right? The lambda or the k over here is replaced by all the characters. And then you use the recipe that the Gauss sum corresponds to gamma function. You can write everything in terms of gamma function. So you can write down the corresponding character sum very explicitly. So a priori, this is defined only for finite fields whose size is going to be 1 modulo M over here. However, in the case when both alpha, beta are defined over Q, Boyker, Cohen, and Mennett define a formula to rewrite the right-hand side of HQ function in terms of using multiplication formula, a refraction formula, so that the right-hand side is independent of the requirement Q to be 1 modulo M. So in that case, we can extend the definition to almost all P's. And in this page, I summarize there are basically 3 functions I'm going to get to later. One is the classical hypergeometric function over C, and the second player is its truncation. The last one is using more or less the same recipe. You can write down a formula over finite fields. All right. Any question before I continue? All right. So I'm not expecting you to follow the full details. I'm just mainly introducing the players. Okay. All right. So here I want to talk about the zigzag diagram for given primitive alpha beta of the same length. Again, primitive over here means AI minus BJ for all the IJ are not in Z. All right. So the way to do it is now we are going to look at all the AI. So modulo Z, we can assume the AI is within the range. It's a rational number. The range is within 0, 1, including 0. BJ is inside the range from 0 to 1, including 1, not including 0. So the recipe is you're going to put them together. You're going to put the 2 multi-set all together. And then you're going to reorder the elements and call them reorder using this order. So you call the first one to be mu1, the second one to be mu2, etc. And then we're going to define a function. The function is defined from the integers from 0, 1, all the way to 2n to z. And firstly, you start with the first value, 0, you set the value to be 0. And then the next one, recursively, you're going to look at the next one, whether the value is chosen from alpha or the value is chosen from beta If it's chosen from alpha, you add one value to the previous value. Otherwise, you drop one value from the previous value. So here I'm giving you one example. I have an alpha set, which is 1/4, 1/2, 1/2, 3/4. You can check that it's defined over Q and self-do. And beta is this multi-set 1, 1, 1/3, 2/3. And if I put them together and list them in the non-decreasing order, so it goes as 1/4 from alpha, 1/3, 1/2, 1/2, etc. So using the definition of this function above, we start with value 0. And if you look at the first value, which is 1/4, is chosen from alpha, so the value go up to 1. And the next value is 1/3, chosen from beta, so the value decrease to 0. And the next value is 1/2, go up to 1. And 1/2 also from alpha go up to 1. And then the next one is from beta, which is 2/3, etc. So you get this diagram. It's called Zigzag diagram. Is there any question about how this picture is computed? And now I'm going to tell you actually how to use this very combinatorial kind of picture. And once you have this going up and down diagram over here, connecting the phi values. So firstly, we can compute the so-called weight function. The weight function will be the maximal phi value minus the minimum one. So for this picture is 2 minus 0, so which is 2 for the current case. And with the zigzag diagram, you can also compute so-called the Hodge polynomial. The way you compute it is the diagram can go down first, so there is a normalization. So you use t minus minimum to make sure it's going to be a polynomial. And then you only count among the values going up and down. You only look at the values where the next value will be higher. So I mark for this picture over here, there are only 4 values. There is an upward trend, including the first one, the second one here, the third one here, the third one here. Then we compute the corresponding polynomial in the way. So the contribution over here will be t to the 0, t to the 0, t to the 1, t to the 1. And you put together, for this case, you get 2 plus 2t. And the recipe actually telling you the Hodge numbers, which is corresponding to something called the Hodge theory or the Hodge filtration. But anyway, I just mentioned those numbers. So once you get the polynomial, then we read off the coefficients. So you consider then to be the Hodge weight to be the total weight you computed minus 1. And so the corresponding coefficient of TQ is called HPQ. For this example, the weight is 2, so we're computing values from H1. And you have this value corresponding to H01 and H10, they're both 2. And this is actually the Hodge numbers for if you compute the corresponding hypergeometric data, which is a generic lambda, avoiding singularity, that's what you should expect. And I'm going to give you an example later. Is any questions so far? Or am I doing too fast? All right.
Does the zigzag pattern always end up at 0?
Yeah, it's actually start from 0 all the way go back to 0 because there are 2 sequences. They are primitive.
Okay.
So they're different. So it's going up and down. So the number of time going up and number of time going down will be the same. Okay. Start from 0 and with 0.
Thank you.
That's a good observation. Thank you. All right. So let me give you one more concrete example over here. So we get back to the 2f1, classical 2f1 function. In this case, alpha consists of 2 elements, alpha, beta, and beta consists of 1 as our convention, and the other parameter will be c. And for this particular hypergeometric data, the formula classically is written as 2f1, referring to there are two variables here, one variable here for the one, and put that this way. So this is the same formula as you've seen before. Here I'm telling you what kind of differential equation it looks like. And there is an important formula which is called the Euler integral formula. The Euler integral formula somehow tells you in order to come up with this hypergeometric function 2f1, a, b, c, and z, you can actually compute this corresponding integral. The integral consists of an integram from 0 to 1. The variable is x. And you let s raised to b minus 1. So it's going to be a rational number. And 1 minus x, and also a rational number. And 1 minus z x raised to another rational number. So this integral in our eye, we consider that as a period. And if you do the normalization, you put out some appropriate gamma factors, what you will get is precisely what we want to study. And now here's the classical kind of relation to number theory, which is actually so-called the Legendre curve. It's actually Legendre curve in a different disguise. So here L sub k in this equation, the setting up over here, k is going to be fixed. All right, so we're going to fix a k, which is going to be a complex number, which is not 0, not plus minus 1. Once it's fixed, then it's one equation with two variables. And it's order 4 in terms of x and order 2 in terms of y. You can think about that as double cover of CP1 parameterized by x, ramified at 4 points. The 4 points are plus minus 1 and plus minus 1 over k. And what you get is actually going to be the structure, topologically, what you will get is going to be an elliptic curve. And if you compute the so-called de Rank cohomology, the first de Rank cohomology of this elliptic curve over C, and it's isomorphic to, so it's going to be differentials. And one of the differential, it's going to be two-dimensional vector space correspond to H1. It's actually, you can computing that from the first homology of elliptic curve if it's non-singular. So this space has two generators, and they are written in terms of differentials on the elliptic curve. The first one is dx over y, which is more or less unique up to scalar because this is holomorphic everywhere. The second one, however, it's not unique because the second one has a pole, so I can always add a multiple of the first one. So in general, there is no canonical choice for the second one unless there is complex multiplication for very special cases. With these two differential, we can actually compute the corresponding periods. In particular, we can compute the differential when it's evaluated from 0 to 1 for the first one. Using more or less Euler integral formula, you can actually get 2f1 with parameter 1/2 on the top and 1 down here, and the variable will be k squared. And similarly, for the second differential, you will get to another hypergeometric function. The variable over here is minus 1/2, 1/2, 1, and k squared. And then, as I said, among these two, this is holomorphic. So this is the one we actually pay more attention to. So they are called complete elliptic integral of first and second kind. And the second one, I want to kind of draw your attention to the relation with the first one. Essentially, the second one, the second elliptic integral of second kind can be attained from the derivative of the first one with some appropriate polynomial of k to the from plus a scalar multiple of the first elliptic integral. And if you look at the corresponding hypergeometric data for this 2f1, The alpha set consists of 1/2, 1/2. The beta set consists of 1, 1. So if you look at the zigzag diagram, if you start from 0, go up, and come down, and come down. So the Hodge polynomial is 1 plus t, telling us that corresponding to a generic choice of k, the first homology of the elliptic curve, actually giving rise, on the cohomology side, there is a Hodge decomposition. The Hodge numbers h1, 0 and h0 will be both 1. And so I mentioned the third player in the introduction will be the finite field analog. All right, just briefly speaking, if you pick a k, which is going to be a rational number, avoiding 0 and plus minus 1, and you have elliptic curve defined over Q. So we know that the elliptic curve is modular, in the sense that you can actually find a modular form correspond to this elliptic curve for a fixed k. Essentially, for Galois representations, one of the important way to kind of identify which one is which is by computing trees of the Frobenius elements. For our applications, if you look at the Galois representations coming from elliptic curves, the trees is actually computed from the finite field, the HP function. And then you use the alpha and beta set as mentioned in the previous slide. So there is the modularity, which is there exists a way2 modular form whose Galois representation will be isomorphic to the Galois representation attaining from the L division points of the elliptic curve L of k. All right, so even though we introduced the HP function, I want to actually mention another version of finite field period function, which is another way to approach the HP function. And the reason is because in our proof, this version is also very kind of convenient. So this definition of finite field period function was kind of introduced in my joint paper with Fuseli, Ravi Ramakrishna, Holly Swisher, and Fang-Ting too. So essentially, it's a parallel to the classical setting. We give a a set of upper characters of A1, A2, and the last one, and lower characters, you have the trivial character B2, all the way to the last one. So these are all multiplicative characters for a fixed finite field FQ. The way you define them is going to be by recursion. Start from the first one, you start from 1. So you only need one character, A1 on the top, trivial character down here. It's defined to be the A1, the multiplicative character. Bar means the inverse or the complex conjugate. You use this complex conjugate of A1 character applying to 1 minus lambda. So this is the starting point. And if you move up the stairs, so if you have already the previous period function, you want to come up with the next one by adding additional column. So what you will do is you use the old definition, and then you're going to submention over everything over the finite field. In front of the old period function, you're going to add the value given by the formula. And now the argument is going to be lambda, which is what you want. And then you let x over the finite field take a product. So you can define the period function recursively, right, which is pretty much tied to the Euler integral formula in the classical setting that I mentioned. And of course, the formula defined over here is purely for individual finite fields, but you can do it in a systematic way. The systematic way of doing that will be if you give us alpha, beta, which is 2 multiplies of rational numbers. Again, m will be the least common denominator. Then we're going to fix one primitive m's root of 1. And then look at the corresponding cyclotomic field will be Q joining zeta m. And then we let the Galois group of Q bar over this cyclotomic field, the notation will be G of M to be the corresponding Galois group, which is the infinite group. And here, for any non-zero prime ideal, P of not dividing the least common denominator. And I forgot to mention about prime ideal. If you take a quotient, if it's a prime ideal, you get a finite field. And for this finite field, I'm going to fix a generator. And the indicator or the way I'm going to choose it will be, I'm going to pick the generator such that when this generator applying to the primitive nth root inside my finite field, it's going to be the primitive nth root raised to the -1 power. So that I'm going to arrange the generator in a systematic way. And in this process, if I create a finite field in this manner, one thing know for sure will be the size of the residual field is going to be 1 modulo n. So we can compute the period functions and all the HQ functions. And here's the shorthand notation for the period function just to save some space. I'm going to write down, instead of this longer notation, we're going to write down P of alpha beta. So the alpha set will be assigned to the top. The BI values will be assigned to the bottom over here using the inductive formula for the P function. And comparing with what I introduced earlier, it's essentially related by the following formula. They are actually all correspond to, they are actually giving you more or less very relating formula. The difference here is by some Jacobi sum. So in terms of Galois representation, they are different by an explicit one-dimensional representation of this Galois group, which is Q bar over Q joining theta n. Okay. And now we're going to see this very useful theorem, which is actually in the work of Nick Katz. And then the last item over here is relating to the recent work of Fitzboykers, Cohen, and Mennett. Essentially, what it gives is the L-adic version for classical hypergeometric functions. So the setup will be you have alpha and beta, and if you have m, which is the least common denominator, and another thing I'm going to mention will be the m over here will be the multiplicity of how many integers inside the set beta. And once you have this setup, then we know there exists a Galois representation. Right? So this Galois representation is actually labeled by HD. It's a triple alpha, beta, and lambda. And lambda is also here for our application. Lambda is going to be an integer, which is not 0. And this Galois representation, basically, it's when lambda is not zero and not 1, the dimension of this Galois representation will be the same as the length of alpha. When it is 1, then it's one-dimensional less. So it's a minus one-dimensional. And another good thing about this Galois representation is if you look at P, which is 1 modulo the capital letter M over here, so the corresponding, the corresponding Frobenius is going to be, the P is going to be unramified for this particular Galois representation. So you can compute the trace of the Frobenius at P under the Galois representation. The trace of this Frobenius element, it's essentially computed by the H function up to a power P and at most up to a character of the Galois group. And when lambda not equals to 0 and 1, the representation is also pure in the sense that all roots of the characteristic polynomial of the Frobenius will have absolute value P to the n-1 over 2. When you get to the singularity lambda equals to 1, it's going to be one-dimensional less, but it's not so bad. Inside this n-1 dimensional vector space, it has a subspace. The subspace is computed by two times the floor function of n minus 1 over 2. So they will be either the same or up to 1. And in the primitive part of this representation, all roots of the characteristic polynomial will also satisfy this property. They have the same absolute value. So it's of pure weight within the primitive part. And the last part will be, and the current setup is for Galois group of this cyclotomic field. In case alpha, beta are both defined over Q. And this representation constructed by cats can be lifted to GQ. So it's going to be Q bar over Q. Of course, if you have a representation which is from finite index subgroup to GQ, it's not going to be unique. But one of the ingredient, one of the lift is given by this work of Fritz-Boykers, Cohen, and Mennett. Essentially, you can use the way they extended the HP function to compute this particular lift that we're going to focus on for our main results. All right. So the essential part of this theorem is very much on the Galois side. There, for given alpha beta, if you let lambda vary for almost all the generic value of lambda over this ring over here, you will have a particular Galois representation. The dimension will be the same as the solution space for the corresponding differential equation. And when you get to singularity, it's a little bit different, but it's not too far away from the generic fibers. And the representation can be lifted to GQ if both alpha, beta, lambda are defined over Q. Okay. And now, before I get to Whipple, which will be the next slide, let me mention about this motivation I mentioned earlier. So earlier in the 60s, de Waal discovered in his famous unit root theory that you can use truncated hypergeometric functions for a fixed P, which is a prime. Again, I'm going to pick a P which is not dividing the capital letter M. And the hypergeometric function is said to be ordinary at P. If you look at the truncation, you only keep K to be 0 all the way to P minus 1 terms, you compute the corresponding value. And the assumption over here is lambda, it's also in ZP. So if you have this value, which is in ZP, you look at what happens modulo P. If the value is not 0, then it's said to be ordinary. In the ordinary case, the Waal notice when beta is going to be this particular multi-cell all ones. And under this assumption, he noticed that there exists a mu P, which is an invertible element in ZP, such that if you look at the truncated hypergeometric series, the difference here in the denominator and numerator will be the P power. In the numerator will be P to the S, where S is an integer, while in the denominator is 1 power less. So it's 2 consecutive truncations of P powers. The ratio is going to be congruent to this unit root modulo high and higher power of P if you let S to get bigger and bigger. The strength of the Waal's congruence will be this will hold modulo P to the S. And in 2017, David Roberts and Rodriguez Villegas noticed that in the case of lambda to be plus minus 1, they noticed in their computation, if A is the unique submodule of the hypergeometric motif corresponding to alpha, beta, lambda, okay, so it's relating to the Hodge polynomial that I mentioned earlier. And one explicit example will be given if time allows. All right, so with the Hodge number of this motif where the truncated hypergeometric series lift, so it will start with 1. And if R is the smallest positive integer such that, so you start with 1, if you have a bunch of 0 in the middle until you get to the next one, which is also 1. And if there is a gap between the first one and the next one, then you can actually get a much stronger condition for the Walk's congruence. So the Walk congruence will be strengthened from P to the S to P to the RS. So the R over here is going to be 1 plus how many zeros in between the two consecutive ones of this hypergeometric submotif, where this capital F lives in. So once the conjecture is out, to me, one of the kind of the challenge will be, how can we construct cases where the gap between consecutive ones will be very large? So this power is going to be very big. And another thing I said to myself is going to, what happens if beta is not always 1? So which will be essentially leading to the main topic, all right, it's a little bit. So the Repost formula, so after the long introduction, hopefully I'll give you some of the motivation. So the Repost formula is actually this version on the screen over here. So on the left-hand side, there's F7F6. And so if you look at the corresponding parameter set, you're going to read it as A, 1 plus A over 2, C, D, E, F, G, etc. And the beta consists of 1, A over 2, etc. So this is the left-hand side. And it's, on the top, there are actually, it's a length 7 kind of parameter set. And right-hand side is another kind of hypergeometric function. The alpha on the right-hand side consists only 4 elements, A, E, F, G. It's a subset of the previous one. And then the beta down here is 1, E, F, etc. And for the 7F6 on the right-hand side, it's imprimative, which means if you look at the difference of these two, obviously it's 1, so it's an integer. They correspond to the same character sum. So when I look at the finite field version, they will be the same, so they will be canceled out. So the left-hand side essentially will be reduced to a 6F5. And if you look at Katz and Fritz-Boyker's, their version of Galois representation, it's at 1. So on the left-hand side, the corresponding Galois representation will be 5-dimensional. And meanwhile, on the right-hand side, because of 1, the representation will drop down from 4 to 3-dimensional. But this identity essentially telling me that for the motif on the right-hand side, a priori is 5-dimensional. Somehow you can read off a 3-dimensional sub-representation that indicates the representation on the left-hand side is going to be reducible. And in order to construct hypergeometric data with good property, including self-dual. And the other thing I want to impose here is going to make the sequence on both hand side to be terminating, in the sense that there is only finite sum, so that the formula will hold. So I actually pick the value. So we pick the value in the following way. A is going to be 1/2. So C plus D is going to be 1 to satisfy the self-dual property. F and G is add up together to be 1. And another thing is the E in the middle. Essentially, we want it to be 1/2. But if it's 1/2, then the series is not terminating. We are getting into trouble. So we do a certain kind of deformation of P. So if P is an odd prime number, 1 minus P over 2 is a negative integer. So both hand side will be terminating. Okay. So let me get to, now after I do the deformation, and we forget about P, when you modulo P, and forget about this 5/4 and 1/4, the difference is 1, corresponding to the same character. Then we read the alpha and beta set of the left and right hand side. The left hand side actually read as 1/2 C, 1 minus C, 1/2 F, 1 minus F, etc. And the hypergeometric data on the right hand side reads as 1/2, 1/2, 1/2, 1/2 F, 1 minus F, and 1, 1/2, 1/2, 3/2 minus C, and 1/2 plus C. So you have two hypergeometric data over here, and the argument both will be 1. Okay. And now when we consider basically good choices in the sense that if I want my hypergeometric motif to be defined over Q and primitive, we end up only have 7 cases to consider. So the list below for the C and F, they're unordered. So if we add the assumption of primitive and divide over Q, there are only 7 cases to consider. Right? And basically the 7F6, you can consider it's very much like the elliptic integral of first and second kind. It's a derivative of the 6F5. After you cancel out the 5-quarter and 1/4, it's the derivative of the 6F5 plus a multiple of itself. Okay. And other players, okay, involved will be, there is extent of the multi-set involving 4 elements correspond to HD2. There is also HD3. I don't think I will have time to talk about it, but they will actually play a very important role due to the Clausen formula. So let me at least get to the May theorem. All right. The May theorem says that for each of the pair, so 7 of them, all right. So there, once you have this, each of the pair CF in one of this list, you can compute explicitly 2 integers coming from denominators of, multi-sets. One is the same as before, is capital M. The other one might be double of this value over here. The reason I might need to restrict my Galois group to an index 2 subgroup is due to the Clausen formula. So basically what it says over here is given one of those one of those pairs in the list, there is one explicit integer. This time is the capital N over here. And when you look at CAT's construction for 5-dimensional Galois representation corresponding to the left-hand side, which is HD1, it actually decomposes into a degree 2 and a degree 3 pieces. In particular, this degree 3 pieces will be isomorphic to the 3-dimensional Galois representation coming from the right-hand side corresponding to HD2 up to a T-twist. So which is essentially parallel to the classical Repost formula in precisely in the format that we would like. All right. I think I'm already out of my time and I won't be able to go over all the slides. I prepared too much. And I will actually give the slides to Fang-Ting in case you want to look at that later. But if you have questions, probably I will take questions from here. All right. Thank you for your attention.
There are any questions and comments?
Well, since you've given a proof in L-adic representations, the classical Whipple formula, there should be a proof using, let's just call it Theorem cohomology or something like that.
Actually given by using the Fach-Shells formula.
Excuse me?
It's not given in that way. It's actually given by manipulating identities.
Yeah.
It's actually using the coefficients, recombine them in a smart way. So it's one strategy which you cannot actually read. It's actually like certain combination of coefficients put together by using certain identity will give you this.
Yeah, that's not my question.
Yeah.
You see, there are many proofs of these identities in that spirit.
Mm-hmm.
But what you're giving here is a proof, as I understand it, using Galois representations.
Right. Yeah. Actually, yeah.
Okay. So I read this formula over the complex numbers and I see Theorem cohomology.
Right.
Of the motive.
Right.
So in principle, I would say, shouldn't there be a proof using cohomology? I mean, a de Rham cohomology. See, I know there's a proof. I mean, Whipple, I guess, gave a proof manipulating some identities. So you've put together an argument, I guess. I haven't seen the argument, but using Galois representations, okay? I guess. So I would say, fine, that's wonderful. Now, is there an analog of such an argument over the complex numbers? But you wouldn't be doing L-adic cohomology, you'd be doing de Rham cohomology.
Actually, when we get to the proof, we go back to see everything in terms of differential equations. There is something pretty parallel going on. I mean, the way we actually compute it is just, I mean, yeah. Well, I guess if we push harder, we might be able to go backward, right? What you're telling me is from this approach, which is the geometric construction, fibers, and etc., going backward. Yeah. Yeah.
So I like to think in terms of geometry of this picture, and yes, I think there is something going on here. But so I don't know. I mean, it's just a question. I mean, and I guess the answer is it hasn't been done.
No, we actually, when we get to the end, everything is kind of amazingly, they come up in all the, like, when we get back to the motivation of constructing so-called supercongruence in David Roberts and Rodriguez related spirit, then we discover indeed using, see the motif, for instance, 1/2 decomposed into 3 motifs. The Hodge numbers are 1, 0, 4, zeros in the middle. The second motif is 2, 0 in the middle. And then there is the, 1, and then so it decomposes into 3 pieces. And then you can get the corresponding supercongruence. And also, there is the Archimedean version. You can actually get to the untruncated version to be kind of periods for the corresponding modular forms.
Right. Well, I guess implicitly in those formulas is such an argument, but it's, I'd have to study your paper much more closely.
That's why I'm giving this talk here, Bill.
Well, just one other general question. You keep using the word motive, and I've seen Rodriguez-Villegas talk about this, and there's even a magma package for hypergeometric motives. And they give all these combinatorial formulas to me, and they never tell me what motive they're talking about.
Yeah, so we have to.
So where is this?
Yeah.
So I mean, fine, you can define these things you call Hodge polynomials, but to me, a Hodge polynomial comes from an algebraic variety. Question: which algebraic varieties are you talking about? You see, and I can't get this out of anything in these publications of Rodriguez-Villegas. I mean, he defines these combinatorial identities, and he just says, well, this is the motive. These are the formulas for the motive. Now, there must be some place where these things are defined. He's got cohomology groups. So what are the references for this?
There are 2 places you can get those motifs from. One is actually using the Euler integral formula. You can get to the hypergeometric varieties. Essentially, it's like legenda curves. It's a ramified covers, and you read off the ramification from the inductive formula.
Right, but those are right, but those are just for curves. Now I'm talking about, see, these are going to be higher dimensional.
For case 3 or for higher, you can do the same thing. So the other reference is actually by Boykers, Cohen, and Menick.
Okay, so you say in that paper they do define.
They have a toric. So it's kind of interesting. What they have is the hypergeometric motif for a lot of application. You're looking at the intersection. What they're actually telling you will be the union. But so they have a machinery telling you a hypersurface. When you compute the zeta function, you get to the motif that you like.
Okay, so I guess it's implicitly in those papers, but I'm going to have to look at these papers more carefully.
Right. Yeah, there are two places you can find those corresponding varieties.
But it's always annoyed me, you know, when I look at this magma package,
Mhm.
and then they refer you to this paper of Rodriguez Villegas, and he gives these formulas, and he doesn't tell you what a algebraic variety he's talking about, what piece of the cohomology he's talking about. He just gives these formulas. And I say, well, why would you call that a hypergeometric motive? There must be some place where these things are defined.
Yes, I think they are using the Fourier's Cohen and the minute kind of approach. Yeah.
Okay, so I have a little homework to do.
Right.